Domain and range of combined functions. Functions f and g can be combined using arithmetic operations. When combining f and g, the domains of both f and g must be satisfied independently. Let's go through an example to help explain this. We're given that f of x is equal to x squared and g of x is equal to 1 over x. Let h be a function defined by h of x is equal to 2 times f times g of x. We're going to first write a rule for h that does not include the notation of f and g, and then we are going to determine the domain of the function h. Let's begin with part A. Write the rule for h that does not include the notation for f and g. So h of x is going to be 2 times f times g of x. That's equivalent to 2 times f of x times g of x. So we have 2 and then f of x is x squared times 1 over x. So now if we multiply these through, we will have 2x squared times 1, which is 2x squared, and then there's a 1 in the denominator here, and 1 times x is x. Notice that x squared divided by x simplifies to just being an x remaining in the numerator. But we also have to add this condition that x cannot be equal to 0, and that's because before we simplified, we have this x in the denominator. And whenever you have a variable in the denominator, you cannot have 0 as the denominator or output of the function. So if I put 0 in this denominator, it will be undefined. So therefore, when we simplify, we have to keep this condition in mind when writing our function. And now to determine the domain for our h function, if we look more closely at the graph, it simplifies to this line, but there's this hole at the origin because we were able to simplify this. And in the original function, again, you can't have 0 as the x value in the denominator, so that's why we have this hole here. It's also called a removable discontinuity. And as you delve further into the course, we will discuss more of this. So then the domain for f is all real numbers, and the domain of g of x is all real numbers excluding 0. So therefore, the domain of h is going to be equivalent to the domain of g because it had that exclusion piece of not including 0. If you were to write this in interval notation, it would be for x is contained in negative infinity to 0 in union with 0 to infinity. Here's another example where we are combining functions and determining the final domain. The functions f and g are shown in the graph below. What is the domain of f plus g of x? Well, let's try to evaluate f plus g of x at various points to help us determine the answer. We know that f plus g of x is equal to f of x plus g of x. So let's try f plus g of negative 3. Well, that's going to be equal to f of negative 3 plus g of negative 3. Well, f of negative 3 is 3 plus the g of negative 3. Wait, there is no g output for negative 3, so this does not exist. Therefore, if we're adding f plus g and it's not defined at negative 3, the addition of these two will also not exist. If we then try to evaluate f plus g at negative 2, that will be equal to f of negative 2 plus g of negative 2. So f of negative 2 gives us 2, plus g of negative 2, there is no g output again for negative 2, so this also does not exist. Therefore, you can't add 2 and it does not exist. It's just going to not exist. Okay, so far we know that f plus g of x does not have a domain with -3 and -2 and the points in between it in there. Let's try f plus g of -1. So if I substitute -1 in for f, we'll get +1 plus, oh, this time g is a point at -1 and it'll be -2. So when we evaluate this, 1 plus -2 will be -1. So here's where f plus g is going to start being evaluated. Now if we do this at 0, f plus g of 0, we're going to get 0 for f plus -3 for g. And when we add 0 and -3 together, we get -3. Okay, now let's try f plus g of 1. That's going to be 1 plus -2. And when we add 1 and -2 together, we'll end up getting -1. And then if we do f plus g of 2, that's going to be equal to f of 2, which is 2, plus g of 2, which is 1, and 2 plus 1 is 3. So then if we connect our dots, it will probably look something like this. Also notice that f plus g of x could only be evaluated where both functions were able to be evaluated. Therefore, the domain of f plus g of x will be that x is contained in a set of real numbers from -1 to +2, including both endpoints. And here's the solution, explaining though this time how the domain of f is from -3 to 2, and the domain of g is from -1 to 2, which restricts the domain of f plus g to be only x values from -1 to 2. We showed why this ends up being possible when we worked this out. It was because we had a value from f, but a value that didn't exist for g when you had -3 and -2 as your x values. So therefore, the domain of f plus g must satisfy the restrictions of both our f function and g function. In our last example, we discovered a property of ordinate addition. Now, an ordinate is the value of the y-coordinate on a coordinate plane. In other words, they're your function outputs, are called ordinates also. And ordinate addition is if a is in the domain of the functions f and g, then a is in the domain of f plus g, and furthermore, it allows that the graph of f plus g, that graph contains the point a comma f of a plus g of a. And let's also demonstrate that with this example. The graphs of f and g are shown in the coordinate plane below. Complete the table and then sketch the graph of f of x plus g of x, which again is equal to f plus g of x. So if x is -2, f of x is at 4, g of x is at -1. So if we add these two together, we end up getting an output value of 3. When x is -1, the f output is 1, the g output is -1. If we add these together, we get a value of 0. When we substitute 0 in, for f, we're at the origin, and for g of x, we're at 1, where the solid circle is filled in, and 0 plus 1 is 1. Now if we evaluate both f and g at 1, we end up having 1 for both those coordinates, and if we add them up, we get a value of 2. For 2, when we evaluate f, we're at 4. When we evaluate g, we are at 1. And when we add them together, we get a value of 5. So now let's actually graph these points. So we have -2, 3. Then we have -1, 0. A 0 value at 1. A 1 value at 2. And 2 is at 5, which is up here. Okay, so this side, we definitely have something that looks similar to the parabola. If we go back to 0 and reevaluate it again for g down here, it would be at -1. So we're going to have an open circle at 0, -1. So that'll help us with the final section of our graph on this side. And here's the solution to this example, and it does match the graph that we had sketched on the previous slide when we evaluated our table for f of x plus g of x, or f plus g of x. Now let's discuss composite functions and how to find the domain and range of these types of functions. Here's an example. We are given the maps of f and g, and we are going to create a map of the composite function f of g of x. That can also be written as f, and then open a parenthesis, and then write g of x inside the parentheses for f of x, and it's still read f of g of x. Since g of x is on the inside of f of x, we have to start with the domain values of g. So let's fill those in the first bubble. We have -1, 0, 1, and 2. And then g is going to try to map to the inputs of f. So this second circle is going to be the inputs of f. And that will be 0, 1, 2, and 3. And now let's use the mapping of g for our first step here. So we're going to map from -1, it maps to 2. That still works. 0 maps to 0. 1 maps to 2. And 2 maps to 4, but there is no 4 in the domain of f. So therefore, this 2 is excluded and no longer counts. Similarly, since 1 was not mapped to in the outputs of g or the inputs of f, we can cross it out. And similarly with 3, for the inputs of f, we can cross them out. And now let's finish the mapping from f. The mappings of f they go from the 0, 1, 2, 3 to 2, 5, 8, and 11. Now 0 maps to 2. There is no 1 that maps to 5, so we can cross out the 5 here. The 2 goes to 8, and the 3 is no longer used, so it cannot map to 11. So this can also get canceled out. So now we have updated domain and range values for f of g of x. The domain is now restricted to be from -1, 0, and 1 to 2 and 8. So -1 maps to 8, 0 maps to 2, and 1 maps to 8. So now let's answer this final question. What happens to the domain and range of f of g of x? Well, we see that the domain has become smaller. So the domain is now only -1, 0, and 1. And the range has become only 2 and 8. So the domain and range become smaller. And here are the solutions to example D. It does verify the solutions that we found, that the updated domain is only from -1, 0, and 1 to 2 and 8, and here's how the mapping works for each set of points, and the domain and range become smaller. The domain for f of g of x is now from include the inputs of -1, 0, and 1, and the range only includes the outputs of 2 and 8. Here's another example on how to find the domain and range of composite functions. This time we are given the maps of f and g, as shown here to the left, and we are going to create a map of the composite function g of f of x. And this can be rewritten also as g of f of x, where f of x is inside of g of x. And remember, when we have composite functions, we need to start from the inside and work our way out. So therefore, the first set of ovals that we will draw for our mapping will have the inputs of f in them. So we have 0, 1, 2, and 3. And it's going to map to g, so we need to put the inputs of g here and the outputs of g furthest to the right. So we'll have -1, 0, 1, and 2. And then we'll have 0, 2, and 4. And now let's go through and see where the mappings take us. So in F, we go from 0 to 2. Okay, 1 goes to 5. Well, okay, there is no 5 in the inputs for G. So therefore, we can cross this input off. 2 maps to 8, but there's no 8 in the inputs for G. So this is also going to go away. 3 maps to 11. There are no 11s in the domain of G. So this input of 3 also does not work. Also, we can see the only mapping that happens is from 0 to 2. So therefore, this -1, 0, and 1 values, they all go away or can be excluded. And now we're going to go from 2, it maps to 4. And then these 2 output values in G are no longer needed. So therefore, the final mapping for G of F will be, we're only starting at 0, and we are mapping to 4 only. Now we can answer this question: what is the domain and range of g of f of x? Well, the domain only includes 0, and the range only includes 4. And here's the solution to this example problem. It maps from f to g, but in a slightly different manner that we used to work out the solution when we worked on it together. They started off still with all of the input values of f, but then they did the full mapping to the outputs of f, and then saw which of those outputs were and were not contained in the domain of G. And they crossed off all of the f output values that were not in the domain of G. And then they looked at G and went from 2 to 4. So the final result for g of f of x is still going to be mapping from 0 to only 4, with the domain being only 0 and the range only being 4. Here's another example with composite functions, their domain and range. This time, we're using visual graphs of functions to complete a table. So we are given the graphs of f and g. We're going to complete the table of the composition of g of f of x. And in the table, it's written the other way, g of f of x being inside of g of x. So therefore, we need to start with f of x first. So for the x value of -2, we're going to have a function f value of +2. For -1, we're at +1. For 0, we're at 0. For 1, we're at 1. For 2, we're at 2. And for 3, we're at 3. And now, let's now take these outputs of f and input them into g. So we're finding g of 2. Well, g of 2 is 1. G of 1 is negative 2. G of 0 is negative 3. G of 1 is negative 2. G of 2 is positive 1. And G of 3, if I go to 3, G doesn't have an output. So therefore, G of 3 does not exist. And now using these table values, as well as the graphs, let's determine the domain of g of f of x and the range of g of f of x. For the domain, we're looking at all of the x values that had outcomes, and those ranged from negative 2 to 2. So x is contained in the set from negative 2 to positive 2, including both endpoints. They both gave us final outputs. And then the range for g of f, that's contained in the set. We have a range from negative 3 to positive 1. And we can also verify this because g is the final set of outputs. We do have negative 3 all the way up to 1, and we include both endpoints. Now remember that since the x value of 3 in the original domain did not produce an output, we do not include it within our domain set of inputs. And here's the solution to our example. All of the values found in the table are the same values that we found when we worked through it. And since the x value of 3 did not produce a final output, that output did not exist. The domain is the set of x values contained in the set of numbers from negative 2 to 2, including both endpoints. And the range of g of f of x is contained in the set from negative 3 to positive 1, including both endpoints. Here's another example on finding composite functions as well as their domain and range. We are given that f of x is equal to x squared and g of x is equal to the square root of x. The first part of this example is going to be to determine a simplified formula for f of g of x, including the domain and range of the composite function. Then we are going to determine a simplified formula for g of f of x, including the domain and range of the composite function. Let's get started. Let's begin by determining a simplified formula for f of g of x. So since g of x is on the inside, we have to take the square root of x and substitute it in for x in f of x. So we're going to have f of the square root of x. So we're going to take that square root of x and substitute it in for x here, and we're going to get that we are taking the square root of x quantity squared. Now we can see that there's this domain restriction that x has to be greater than or equal to 0. Some of you may be asking, where did that come from? Why are we saying that? Well, that's because we have to start from the inside of the parentheses and inside this innermost function. And if we were to put, say, a negative 2 in for x, you're not going to have a real output for the square root of negative 2. It's just not going to happen. Same thing with negative 1. If you put negative 1 in for x, you would not get a real output. So therefore, we have to put this domain restriction that x must be greater than or equal to 0. And that helps us answer the first part of the question. What is the domain of this composite? Well, the domain is of f of g is going to be that x has to be greater than or equal to 0. And then if we simplify the square root of x raised to the second power, well, the square makes the square root go away. So we just have x for the domain restriction that x has to be greater than or equal to 0. So that's going to look like a straight line, starting at the origin and continuing with a +1 slope. Now the range, because the domain has to start at 0, the range also is going to be starting at 0. So the range of f of g of x are all values greater than or equal to 0. Now let's look at the next example. We have to determine a simplified formula for g of f of x, including the domain and range of this composite function. So this time, f of x is the innermost function. So we're taking x squared and we're substituting it into g of x. So we're doing g of x squared. And when we take x squared and we substitute it in for x here, we're going to have the square root of x squared. This time, the innermost operation is x squared. So if you substitute in a -2, -2 squared will be +4. And then when you take the square root of 4, you will get a +2 output. So as we have just found out, the domain of g of f of x ends up being all real numbers because you're taking the negative number and you're squaring it first, which will make it positive. And then you are square rooting that positive number. And since there is no sign out in front of the square root, it is assumed to be positive. Therefore, the graph of g of f of x will be the square root of x for all x values in the real number system. Therefore, the range of g of f of x is going to be g of f of x has to be greater than or equal to 0. It's going to be identical to the range of f of g of x. And again, that's because if you substitute a -3 in for x, -3 squared is +9. And if you square root +9, there's no sign in front, so it's automatically assumed to be the positive output, so it will be +3. So that's why it maps onto the absolute value of x function. To determine the domain and range of composite functions takes time and careful analysis. And here are some guidelines that you can take into consideration. The first one is that the domain of the inner function must be honored in order to begin. So remember when we had the square root of x, and that in and of itself was being squared, we had to take the square root of x's domain, which is that the x values had to be greater than or equal to 0, into consideration. The second guideline is that the inner function's range becomes the outer function's domain. It too must be satisfied. In honoring this, the domain of the composite function may have restrictions beyond the inner function's domain restrictions. You may want to use a map, a table of values, or a graphing utility such as Desmos to aid in your inquiry. In short, this is not a simple matter. It does require some analysis and understanding of function behavior.